Hey guys, today we're going to be looking at a bunch of examples for sequences Year 12 applications. They're in no particular order, and I will put some timestamps so you can skip through questions in the description for the video. So, most of this is just going to be me talking through each question out loud, and when I can think of it, some common mistakes that you might see or make. So, let's start with question 1. Write the defining recurrence rule for each of the following. We've got a sequence, and essentially what I'm going to be asking myself is, am I adding, subtracting, or am I multiplying or dividing? Now I'll use the signs, that might be a bit better. Add or subtract, multiply, divide. Difference is that these two are going to result in an arithmetic sequence, and this will be a geometric sequence. So depending on which one I'm going will change how I form it. Okay, so this looks like I'm adding 2 repeatedly, and I am doing a recurrence rule, so I'm doing the pattern. I want Tn plus 1 or Tn in terms of the previous term. So Tn, and I am adding 2 regularly to the pattern. Any recurrence rule is incomplete without the first term. T1 is equal to 14. Occasionally you might use T0, but in this case there's no need. 64, 32, 16, 8, 4. This looks like I'm halving each time. You can check your common ratio, remember, by your next term divided by the previous term. That little idea there. Okay, if it has a constant ratio, then you definitely know it's geometric. I'm pretty sure this is half, so I'm just going to write, and you could as long as these numbers, the subscript is 1 apart, or this right hand side is 1 less than the left hand side, then it's a fine rule. Anyways, question 2. Calculate the first 4 terms of the sequence given by the following recursive rules. So again, we've got a recursive rule, we've got our first term, so really we only need to find 2, 3, and 4. Okay, T1 is equal to 4, T2 is equal to 2 lots of, and what I'm doing is T1 plus 3, so 2 lots of 4 plus 3 is equal to 11. So I'm just replacing the previous term's number in here. So T3 will be 2 lots of 11 plus 3, which is 25. T4 is equal to 2 lots of 25 plus 3, that's equal to 53. So I've got, I'll highlight it, T1, T2, T3, and T4. Cool, I think we're done with that one. We've got our first 4 terms. This one's a little bit trickier, and what we want is trickier because we've got 3 terms. And you've got to pay attention to the subscript difference. You might want to do a couple of examples. Substitute values for n. So if I said let n equal to 2, for example, then I would have u3 take u1 equal to u2. So this term in the middle is too different than the next one. So it might be easier if I do my rule as un plus 1 is equal to un plus un take 1. So I've just added un take 1 to both sides so that I have the highest numbered term on the left-hand side by itself, making my rules a little bit easier. So got u1 is equal to -1, u2 is equal to 3, u4, 3 is going to be equal to u2 add u1, which is equal to 3 add -1, which is 2. And running out of room here, but u4 would be the previous two terms added together, so u2 plus 3, u3 plus u2, in case you're unsure, and that's equal to 5. Okay, so again, I'll quickly highlight my first four terms, u1, u2, u3, and u4. There's the first four terms of each of those sequences. Okay, question 3. We are looking at long-term solutions for Tn. So with long-term solutions, you can have a few different ideas. You can have it approach positive infinity. Okay, it gets increasingly bigger. You can have it approach negative infinity. Okay, it gets increasingly large, but in the negative side of things. You can have Tn approach some number. Okay, that's your steady state solution. And you can have Tn approaches not much at all. Okay, this is usually when it's bouncing around. It goes from positive to negative, and if it's going off in both directions, it's not approaching any one number. So you don't say it's approaching anything. You say it's not approaching anything. Not approaching anything. Or better yet, no solution. Okay. Not approaching anything, in case you're unsure of my handwriting, which I would be. So let's go through a couple of these. So it would be easier if you just have a bit of an idea of what's happening in your pattern, so maybe do the first few numbers, okay? Steady state solutions have a very particular idea as when r is between, -1 and 1, okay? And r is not 0, because then that's kind of useless to us as a steady state thing. So if r is between -1 and 1, so it's a fraction usually, then it would generally lead to a steady state solution like this one here. This is likely to lead to a steady state solution. We're going to treat that problem slightly differently. But this one here seems to be ever increasing, okay? So for example, T1 is 0.5, T2 is equal to double half is 1 plus, so we've got 5, double 5 plus 4 is 9, and it's just going to keep getting larger and larger. So Tn is going to approach positive infinity. Now for a steady state situation, again, we can recognize it because that number in front of this pattern here that was formed, my r value, is a fraction. So how do I do this? I'm going to treat Tn and Tn take 1 as the same number, which I'm just going to call x. So I've got x is equal to 3/5 x plus 12. Take 3/5 from both sides, which would be 2/5 x on this left-hand side. Add 12 on the other. Okay. I would need to times by 5, gets rid of that part of my fraction, and then divide by 2, gets rid of that part of my fraction. So x is equal to 30. Tn approaches 30 in the long term. Okay. We have question 4. For the following sequences, find the 51st term. So if we're jumping many terms, okay, we would want to use the general rule or the non-recursive rule. Non-recursive rule. So we have recursive rules where we have Tn in terms of the previous term, or Tn plus 1 in terms of the previous term. It just tells you the pattern. That's a recursive rule. Non-recursive rule is generally some sort of equation where we have Tn in terms of n. Okay, and so we have two types of rules here. We've got arithmetic and we've got geometric. Your arithmetic looks like Tn is equal to a plus n take 1 d, where a is your first term, or t1. If it's t0, this rule actually changes a little bit. Okay, and d is your common difference. Geometric looks kind of similar. We've got r to the power of n take 1. Okay, brackets around that in case you're using a scientific calculator. You want to make sure that you have your brackets there. Cool. A is still T1 and R is your common ratio. There is no rule to jump terms when we have a first order linear, okay, which is when we're both adding and subtracting and multiplying and dividing your previous term. All right. Let's go through the actual question. 54, 52, 50. Well, I'm taking 2. So my common difference is -2. And you could check it with Tn plus 1, take Tn. That whole idea. I can be pretty confident in that though. And we need our first term to fill in my rule. It is 54. Okay. Clearly it's arithmetic because I am constantly taking 2. We have a common difference. So I'm going to go Tn is equal to a 54 plus n take 1 times by my common difference. And you need to put that negative in. Sometimes it's forgotten, and that's when you're generally going to have mistakes. We want to find the 51st term, so if I put 51 in for n, then 51 appears on that side in place of n as well. We've got 51 take 1 is 50. 50 times by -2 is -100. So I've got 54 take 100. That's equal to -46. Okay, so that's my solution there. T51 is equal to -46. Okay. Cool. Next part. We've got a GP. This stands for geometric progression. So this one actually tells us it's geometric, and it tells us the ratio 2. Now this one's a little bit trickier because we've got a ratio of -1, and 1's tricky in the way that it just kind of, or negative makes it flip-flop. 1 means it doesn't really change. So what I'm going to do is have a quick, I'm just going to write down the sequence for what I know here, okay? I have 7, and then it would become -7, because I'm timesing by that -1, 7, -7, 7, -7. It's going to keep repeating that pattern. So I've got T1, T2, T3, T4, T5, T6, and we want the 51st term. And what you might notice is that your odd values are always positive. So if they're always positive, then T51 is also going to be 7. Cool. Question 5. A sequence follows the rule Tn plus 1 is equal to 3 lots of Tn plus 1. If T4 is equal to 67, what is T3? Well, T4 is equal to 3 lots of previous term, T3, plus 1. We know what T4 is equal to, so we can substitute 3 lots of T3 plus 1, and then it's just a matter of rearranging to go backwards. So take 1 first. 66 is equal to 3 lots of T3, and so dividing both sides by 3, we get 22 is equal to T3. Okay, that's the important part. You have to remember that your next term is equal to some multiple of your previous one. Well, these two are very close together. If you needed to go back to T2, then you would go T3 is equal to 3 lots of T2 add 1. And go backwards again, following the same pattern. Alright, last one for the non-calc section gets a little bit trickier, okay? We have terms 2x, 4x plus 1, and x plus, take 3, form an arithmetic progression, or arithmetic sequence. Sequence progression, same thing here. What is the value of x? So, what's special about an arithmetic progression or sequence? We know that it has to have common difference, which means that Tn plus 1, take Tn, is my common difference D. Which is important because we have 3 terms, which I'm just going to call T1, T2, and T3. So when I do the next one, take the previous one, I should have the same number. So T3 take T2 is equal to D, which is also equal to T2 take T1. Both of those terms should be the common difference. So let's substitute. We've got 8x take 3. When we're taking a value, generally it's good to use brackets. 4x add 1 is equal to T2, 4x add 1, take 2x. I won't worry about it there because I don't have to expand those brackets here. So remember that this minus is going to apply to both terms when we need to expand it and simplify to find x, because we need to make x the subject. That's the goal. We need to find what is the value of x. So I've got 8x, take 3, take 4x, take 1. Usually the common mistake is that people don't apply that negative to the plus 1 as well to make it negative 1. And that's going to affect things later on. That's where the mistake is going to happen. 4x, add 1, take 2x. I'm going to collect like terms, so I've got 4x, take 4 on this side, and 2x, add 1 on this side. Get x's to the one side is my next goal. So I've got 2x, and I'm going to skip a step here. I'm going to bring the negative 4. I'll get rid of the negative 4 here at the same time. The opposite is to add 4. So I get add 4 to both sides. 1 plus 4 is 5. X is equal to, opposite of times by 2 is divided by 2. You can write the fraction or the decimal if you like. you know what, I will chuck in that extra step just in case. 4x take 4 is equal to 2x. Oh, sorry. Scratch that. 2x take 4 is equal to 1, and then I would add 4 to both sides to get this next step. So I've gone from there to there, and then back to there again. Anyways, that's the non-calc section, and I will put up a part 2 for the calc section.